Okay, we can move it. Okay. Yeah. So in the question first, what is that? Question first is that in the question given below, there are two statements marked A, assertion and reason R1 and R2. Mark your answer as per the options given below. Assertion A, the gain equalizes the loss in a laser cavity under steady state conditions. And reason R1 is given as the excess pump photon in a laser cavity steady state contribute to signal photons. And the reason R2 is given, the excess pumped photons cannot sustain in the cavity. Okay. So what do you think, like guys? You can just give like hint how it is possible or what could be the answer for this, so I can explain properly after that. Since it is a live now, so better to ask first you guys. If you know answers, then we can move forward. What do you think? Like, what could be the answer for this? Sabapati is there. Anirudh is there.
Yes, sir. I think
Yeah,
assertion is right.
assertion is right. Okay. So, like, reasons, can you tell me? Rahul, what do you think about this?
Assertion, uh, because I think R1, reason R1 is correct.
So, why you are telling R is correct? Like, some specific thing?
Because pumped photons uh, can populate more, and hence emitted photons which are in the signal photon range, signal photon count will also increase.
Yeah. So, there are three as the signal photon is the main factor. Okay. Okay, so actually, like whatever you are telling, like it is correct only. Like how you are telling, that is like the excess
Yeah.
sperm photon in the cavity contribute to the signal photon.
Ah,
Okay, it will directly contribute to signal photon, and while maintaining the
okay.
cavity gain equal to the loss. So whatever the loss it is making, it will maintain
Yes, sir.
cavity gain. It will maintain cavity gain. Okay, so yeah, that is correct of reason. So like automatically the reason 2 will be like incorrect, become incorrect. So there is no it is it doesn't have talked about um, incorrect reasons here. Okay, directly it is asking about A is correct or not. So A is correct everywhere, and the thing is second reason
Yes.
2 is reason 1 is correct. So the first one is only the correct option.
Yes.
Okay. So Anirudh is telling 3. It is not correct because
Yes.
what is happening here? This excess photon, it will contribute to the cavity gain. Okay. Whatever the loss it will make, it will gain again.
Okay.
So yeah.
Hmm.
So that is quite
Hmm.
simple
Yes.
question and easy also. Yes. Okay. Now this question number 2. Here the question is at the line center of lambda naught is equal to 694.3 nanometer transition. The absorption coefficient of rho B in thermal equilibrium, that is without pumping at 300 Kelvin, alpha V naught is equal to nu naught is equal to minus gamma nu naught is equal to approximately 0.2 per centimeter, and the concentration of the of the active chromium 3 plus ions responsible for the transition N naught is equal to 1.58 into 10 to the power 19 per centimeter cube. Determine the transition cross section. Sigma V is equal to sigma nu naught and it should be given like xx dot yy and 10 to the power 19 per centimeter into 10 to the power 19 per centimeter. So in this, what they have asked is a simple cross section, transition cross section they have asked. So what could be the transition cross section? A second. Sigma naught is equal to, what is that? Absorption coefficient, mu naught upon Na. And we know that, sorry, Na, it's not Na, it's a N naught we can say. So if you write down everything here, you'll get the, we have given this alpha naught value and N naught value. That's the simplest question. Did you got the answer? Can you just try to solve this so we can confirm that? One point 1.16. Like some mistake you are doing, Anirudh? It's given here. This alpha and V naught, alpha and U naught is there, zero point 0.2 centimeter, 0.2 per centimeter, and this also is there. Just you have to divide. Which minus sign you are talking about? No, it's alpha V naught is a not minus. It's positive only. That is given in the like gamma value. You guys just calculate. Yeah. 8.5. So the answer, whatever the answer will come, that should be xx dot yy means after this dot you should be having three, after decimal you should be having three values into 10 to the power minus 19. Now it's quite easy. Guys, you tried. Anirudh, you tried again. I think you have shifted some values front. That is correct only, but yeah, that's correct. Okay. So this one is the correct option of answer of this. Okay, it was quite easy question. You feel that? Please do this kind of questions in like main question paper also. This is assignment only. We have to solve in main question paper. So please be prepared for that also. Okay, now this common data for the question 3 and 4 is given. In that, what is there? A laser makes use of a 10 centimeter long gain medium of 1 centimeter square cross sectional area. Both of its ends are polished and coated so that they have a reflectivity of 80% each. Neglect any other scattering or other extraneous losses. So we have one cavity. Okay, this is cavity 10 centimeter long, 10 centimeter long, and this cross section we can say that is 1 centimeter square. Now both of the side, this both side, it is polished, and that made like it should be reflect at least 0.8 or maybe 80% we can say both side. Okay. Okay. So 80% both sides reflectivity is there. Now question number 3 is that determine the resonator loss coefficient alpha r in per meter. So what could be the resonator loss coefficient and how what is the formula for that? You know guys, alpha r is equal to alpha internal, whatever the loss internal is making, and alpha mirror. Okay. So as given here, this that neglect any other scattering. It means like internal scattering is not there. So this term we can just tell that should be 0. Only the mirror loss, what we can say. Okay, loss coefficient we can say for this mirror only. So how you can determine this? That is alpha mirror is equal to 1 upon 2L ln 1 upon R1 R2. Now you have everything. Length it is given already. L and reflectivity is given already. R1, R2 both are there. Just calculate once. What could be the answer for this? Yes, February correct. Yeah, correct. Yeah, you just change unit you have to take care of that. It's in centimeters, so meter you have to convert in the last. First you do with centimeter only. In the end you can convert into the meter. There is no issue. Okay, this one is that. So just solve this. We'll check the answer is correct or not. Yeah, approximately. Yeah. So it is in a meter. Okay. You have to write unit also because sometimes some students have done mistakes in assignment. Sometimes it is asked in per centimeter or centimeter. They have given in meter or per meter. Okay. Like that it can be happen. Yeah, you are right. So unit also you have to write. Okay? Like here, not an like fill in the blanks. That will be value only. Then question number 4 is asked. It is it has been asked that the determine the average lifetime of a photon in a resonator in nanosecond. So resonator lifetime, how we can calculate that? Do you know any formula for that? Lifetime? Yeah, that's correct. That's what then. How to type? No. You don't have to type there. Don't worry. No. I'm telling here only. If you are typing here 2.231 per centimeter inverse, then how I'll understand that it is like either you are typing per centimeter or per meter. That's why. Okay. Okay. 1 by C alpha. Yeah, you are very like nice. This correct. This is correct. So you just keep and you'll get the lifetime. Okay. Tau. Nicely, you guys are copying up. I thought that last time it happened, nobody was giving answer. So tau p 1 upon c alpha. So this is for question 4. How to solve 16.175. What is that? Oh, what like what you're doing, Harshvardhan here? 16.175. Okay, you just correct it. So it should be in nanosecond. So first of all, it will come in second. Then uh, problem is there, guys. Then it should be 10 to the power minus 9 second. So so it is asked in nanosecond. So whatever the value you are getting, just let me know first. Nirud, are you doing that? Subhapati,
I think it's 1.49.
1.49. Yeah. Yes, it's correct. Almost 1.493. Okay. No, not 140. Nirud, not 149, 1.49. Maybe you have like two decimal you have to shift every time, huh?
Okay.
Okay, it's in nanosecond. So yeah. So now this question number 5 will go. Question 5 is saying that what should be the small signal population density N naught of a gain medium in terms of the threshold population density NT, so that the photon flux density phi from one of the two ends is equal to the saturation flux phi s. Okay, so here it is quite easy like problem, and thing is like you have to do reverse, then you'll get to know like is it like what is the relation between this photon flux density and photon saturation. Okay, did you get my point? First I'll just write here, it is given that the photon flux density, right? Yeah, photon flux density phi the nu is equal to, do you have calculate like solve this problem? Okay, put in the solution of to the question, right? I didn't get you. What is that? Put in the solution to the question. Yeah, sure, 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 sure. You have already solved this, na, previous one. So question number 5 we are solving now. Yeah. So question number 5 is 5. Just try first. I will just after that I will let you know. Like it will be easy for you guys. How much you can do, I can understand with this. Hmm, I think uh, Anirudh, it is how you have calculated this. Like the simple way, simply one equation you can write here in chat box. Okay. Yes, you are correct. So I'll just write in another way. See, yes, new into n naught upon nt minus 1. Okay, this way also we can write this. Then, in that what we have done, like we, what happened? Something? Yes, yes, you are correct only. Okay,
2nt, 2 times n suffix t.
no, it should not be 2 times nt. I'll just solve this problem. I'll tell you. Okay, what is happening? We have to keep one by one this n naught value. Okay, this all the values we will keep one by one, and we'll see. So first I'll start from this nt by 2. So if I'll keep here nt by 2, what will happen? It will cross like this, then minus 1 by 2 will get, and that will be phi v is equal to phi s, and that will be minus, sorry, here I forgot, like this. Okay, that is not correct actually. So it is that photon plus density from one to the one of the two ends is equal to the saturation plus. That is given, condition is given. So what could be the what could we get? We should get that photon plus density should be half of the like the density emitted from one of the cavity ends is half. Okay, so whatever the phi s should be there now, the saturation plus, it should be half. This condition we should get. So which in which n naught value will get this? So we'll keep another one, this one nt directly. So nt will get 0. This 1 minus 1 it will come, and that will become 0. 5 is equal to 0, or you can say another vice versa also. Then what will be the another possibility? We'll keep this 2t. So I'm keeping here 2t. So what is happening now? We are getting like this. 2 minus 1, so 5s we are getting. Okay. Another possibility is 3. So we'll keep here 3. So if we are keeping 3 here, then what is happening? We are getting 2 here. And 2 means it will be is equal to this one. So like that we have to do. We have to solve, and we should get the photon plus density from one of the cavity ends should be half. Did you got that? Because it should be totally full, like 5 equal to 5, both side, if we consider. Yeah, one side only we are taking, like one of the cavity ends. So one end it is half 5 by 2. So another end also will be 5 by 2. Like that we have to think. Okay. Now I'll move toward the next question. So you got it? What could be the answer? Okay, question number 6 will go. Number 6 is what should be the small signal population density and not of a gain medium in terms of the threshold population density NT for the gain coefficient to decrease to half of its small signal value. So here again it is asking what is the relation between this gain coefficient and photon plus density? Can you tell me? Gain coefficient. Do you know, guys? Like, can you write down? in chat box. Okay. So then the gain coefficient, it will be gamma nu is equal to gamma naught nu upon 1 minus, 1 plus 5 upon 5s. Okay, 5 upon 5s. That is the relation. Now here you know that what is given, the gain coefficient to decrease to half of its signal value. It means what? If we'll give this gamma should be half, it is asking. Gamma will give gamma is equal to half. Keep here. Then what you'll get, the phi and phi s relationship. Just check once what you are getting, the relation between these two. 220, yeah. But first, step by step, we'll solve, then better. Rahul, first you solve this. What is the relation between phi and phi s? I think I made one mistake here. It should be gamma naught by gamma naught by 2. Yeah, this should be reverse. Sorry guys. Yeah, now you keep. Did I make some mistake? Yeah, both are equal only. It should be, if you'll keep here, phi should be phi s. Okay. Then if you'll keep these two values in a previous question, previous formula here, okay, this both will cancel out, and whatever you'll get here, you have to solve that. So in that you will get the n value, exact value of n naught. Okay. So your answer will be here. Yes. This one your answer. Okay. So that will be become like this. Okay. In the end, it will cut 2 minus 1, 1. Got it? Yes, sir. Then it will be phi is equal to phi s. So that's why this condition is given in coefficient, gain coefficient. Then you have to convert into the photon flux density. If you will just practice this, you will get to know. Like that is not an issue. Whatever the solution, like lectures are there, in that everything is properly explained by professor. This whatever we are taking this questions, assignment questions, it is taken from this directly from video lectures. So that is not an issue. If you'll solve, if you'll do, yeah, it is hard, but you have to remember. We can't do anything. In the final exam, you have to be remember these things. And that will be in particular centers. It won't be like online or something. Okay. Then question number 7. Question 7 is saying in the question given below, there are two statements marked A, assertion and reasons R1 and R2. Mark your answer as per the options given below. Assertion A, the location of the peak amplitude of any of the longitudinal mode does not change inside the laser cavity. And reason R1 is given as the laser oscillation condition corresponds to constructive interference condition in the laser cavity. And reason R2 is given the frequencies that do not correspond to longitudinal mode of a laser cavity experience loss and get diminished. So, what do you think? Like, assertion is correct or not? First of all, it's already written in this all the options that assertion is correct. So we can say that the location of the peak amplitude of any of the longitudinal mode does not change inside the laser cavity. Why it is not changing? Since it is a constructive interference criteria it is having, and that is making the standing wave patterns, okay, inside the laser cavity. Got it? It's a fabricated kind of laser, okay? You can say longitudinal modes means. You got it? What about the reasons? What do you think? Like both reasons? Yes. Okay, both are correct. Huh? How you are justifying this R1 there? The laser oscillation condition correspond to the constructive interference condition in the laser cavity. Yeah, constructive interference is happening. That's why the standing wave is generating and then the lasing is happening. Okay, so we can say that R1 is correct. There is no doubt. What about this two? Yeah. So the frequency that do not correspond to longitudinal modes of a laser cavity experience loss and get d- diminished. What that means? See what is happening here. This frequency is not playing a role because see whenever you are make like it will be standing wave and you are changing the position. You are not changing any position here. Only what you are changing here? Time is the changing. Like particular time we are getting this constructive or destructive. Okay, the location is same. I'm just show you here. You see first. Suppose we will get one. We have one Fabry period, and we have constructive and destructive interference. You just assume that like this. Again, it will come back. Oh, sorry. Okay, just assume that Fabry period is happening. Right. So what is happening? The particular place it will hit this side also like this. So location will be same. But the time is changing. Okay. So what we can say that a standing wave oscillates in time, but the location of its peak amplitude does not change. Okay. Standing wave will be like, yes. So then temporal variation is that bad. Is not what you're telling. If location is not changed, then temporal variation is tracked like that. Actually, the thing is like in this, yeah, I didn't get your word like not change or change actually. So so you are agreeing that point like with time the standing wave is location is not changing. That's it. So here this reason two will be not correct option. Whatever Rahul has said are two that do not correspond with the that frequency does not do not correspond to the longitudinal mode. Hmm. Yeah, only that oscillation condition is corresponding. Okay, so did you got this point? So option which option? Option A is correct here. So the uh, question number 8, it's written that in the lab experiment video, a ring laser is constructed using an erbium doped fiber as shown in figure as shown below figure 1 match the different block with the corresponding optical components. Option 1. Yeah, option 1. Okay, question number 8. Just tell me the what is the A component here? You can easily understand this one. What is the option B? Like here, B is given. P is what? Y, X, Y, Z, W. What is that? B. Is it a pump laser or a coupler or a filter? Can you guys just as give hint? Yeah, somebody. Anirudh? Yeah, Dhruv is there. Pump laser. B is or B you are telling or A? Dhruv? It's B or A? Okay, B. Yeah, it's correct. We are having this B laser. What about A? A, WDM, Rahul. Yeah, it is correct. A is WDM. What is happening there? It should be like a resonator here. So whatever the input is coming, it will go this direction also, this direction also. or maybe it will be this direction as well from this. Yes. Now, C, what do you think about what do you think about C?
It's coupler, I think. Coupler.
Coupler. Which coupler?
50-50 coupler.
50-50 coupler. Yes. 50-50 coupler because output is going to 50% output is going this side like this. Okay. Then D.
I think
Harshvardhan is telling something. Wavelength dependent multiplexing will convolute wavelengths. Regarding this one, you are talking about
50 coupler. I think is it WDM?
option like which one? D or which one you are talking about? Particular wavelength. Seems actually, thing is like till here it is correct only. You can assume that there itself. What is happening? Laser, D is laser, that is input source. Then it is going to the A. A is what? WDM coupler. Then what is happening? It will go to the 50-50 coupler. Here it will split, and one signal will go to output, and another will go to the this one D side we can say. And what is happening in
C.
D? Yeah, C from C to D side. So D is what? Then fiber back grating filter only. Are you getting that?
Yes, sir.
Hmm. So it is like a one kind of setup. Setup for ring laser. Okay. Near circulator. Just a second. I'll just check my voice. I think now it will be okay. Yeah, please allow me this time. Next time I will change. Maybe it is now okay, I think. Okay, did you got that? All the options. Are you agree with me? Okay. Now we'll go for the question number 9. In question number 10, both are having common data. So the common data of question number 9 and 10 is a laser cavity of length 1 centimeter has an average photon lifetime of 2 into 10 to the power minus 9 second and mirror reflectivity R1 and R2 of 1 and 0.98 respectively. Mike, Harshvardhan is having some doubt in this. No, it is a match the different block with the corresponding optical component. You have to match this. A, B, C, D is there, na? With X, Y, Z, W. I didn't get you what you are telling. Option B is looking good for ring laser. Harshvardhan, option 2. And the question number 9 you are talking or 8? Option 2. Here there is no such kind of option. See, A is there. Okay, okay, okay. So A is there. A is WDM coupler. Here you have to assign this component name that is there. Okay. So A is here WDM coupler. B is like pump laser. C is what? C is here 50-50 coupler. And D is fiber Bragg grating filter. Okay. Now you got it? Okay. So here we were there. Determine the slope efficiency of the laser. So how you can determine the slope efficiency? Slope efficiency formula eta E is equal to C tau pH upon L 2L. ln 1 upon R2. Why only R2? R1 is 1 only. You can write R1 R2 also. There is no issue. But only one side, this mirror reflectivity is a little less, 0.98. The other side is 100%. Just solve this. Everything is given there. C is like speed of light. Tau is lifetime. L is given 1 centimeter. And R1 R2 is given already. Yeah, calculate. Point 606 almost. Okay. Wait, I'll check. Just second. Okay. So where were we? Yeah. So correct answer is Rahul. I think you have done some mistake. Oh, you are talking about question number 10. Oh, you are very fast. Yeah. So question number 9 answer is correct. 0.606. Yeah. No, you don't have to worry about this percentage. It is not asking the percentage. Just write down the numerical value. Okay. Now this question number 10. Something they have tried. Rahul and Harsvardhan. They didn't got. That is here. What is asked? Yeah. If the threshold pump power for the above laser cavity is 50 milliwatt, then calculate expected out power at a pump power of 200 milliwatt, and that should be in a two decimal value, up to two decimal values. So just a second. So here output pump output is like what is the power output is coming, that we have to calculate. How we can calculate? Theta E, whatever the slope efficiency we are getting, minus P. P means what? Whatever the pump power we are giving, minus P threshold. At see what is the threshold pump power? Threshold of this. Okay. Now you try. Yes. I feel you got it now. It's very easy. Just write down that 200 minus 150 means 150 milliwatt. Into you have to do that eta E value, that is 0.606. Yes. Yeah, yeah, yes, yes. Yeah, almost all are correct. Yes. Okay, so you got it. Today's session was helpful, I think, for you guys. Yeah, so please, if you are having any doubts, I'll just send you one link. Try to ask questions if you have any doubts or any problem. Today, professor supposed to join us, but maybe he's out of station, I think. So maybe he will join next week. Okay, this uh, form I have given. Okay, maybe I don't know. Yeah, he's not replying. Maybe he's outside or now. He told that he will join IDEO also, but not yet. Okay, so just try to fill this form. Like whatever the questions you have, I have asked your name, mail ID, and that question. I have multiple question also. You can write down in that and submit that. So whatever the questions we'll get, we'll just answer that. And keep learning, guys. Like it is very useful for you. This photonics videos. It is a you are telling that uh, formulas are difficult to remember, but yes, it is basic only. You have to remember those things for future if you want to continue in these things. Okay. Yeah. Okay, Harsvardhan. Okay, guys. Yeah, yeah, yeah. I'm also not like exactly the photonics. I'm having a material scientist, material chemist as a my topic, material chemistry. So that is a quite different thing, but I haven't taken this. So if you learn, then you will get very easily the things whatever the professor is doing. Yeah. Okay then. Thank you guys. Bye bye.